Today we're going to do a somewhat different myth than we might. It's an odd myth. It involves something called a trebuchet. Now a trebuchet is actually a French catapult. The idea of a catapult is to throw a projectile long distances, generally to break down a castle wall or something of that nature. The difference between a catapult and a trebuchet, though, is that while a catapult uses tension, so tightening a rope and then letting that energy throw the projectile, a trebuchet actually uses a counterweight and its gravitational potential energy to throw the projectile. And therein lies our myth. The myth is that if you increase the mass of the counterweight, the projectile will keep going further and further as long as you increase the mass of the counterweight. Now that makes sense. I mean, as you raise the counterweight, you are giving it gravitational potential energy. If you increase the mass of the counterweight, then there's more gravitational potential energy. Therefore, more energy to throw the projectile with. But later, we're going to find out, when we bust this myth, that that isn't quite true. Our controls for this myth are: the projectile is going to be the same mass, the throwing arm is always the same, which means it has the same ratio between the short arm and the long arm. The counterweight is always going to be falling the same distance as per the throwing arm is going to be the same. It's falling the same distance to the floor, traveling the same distance to our target area, so the trebuchet is going to stay in the same position. Our only variable is going to be the mass of the counterweight. We're starting with it as 100 times the mass of the projectile, which according to a calculation should produce the best results. Then we're going to go to about half that mass, and it's going to show that the mass of the counterweight does matter, and it's going to go a much shorter distance. And finally, we're going to increase the mass many times over 100 times, and we're going to show that despite increasing the mass, it doesn't go much further, therefore busting the myth. 3, 2, 1. Two, 1. Two, 1. Now that we've done 10 trials with a counterweight that is 100 times the mass of the projectile, we're going to measure, record, and move on to the next counterweight. So now we've increased the mass of our counterweight to many times more than 100 times the mass of our projectile. Now, according to the myth, these projectiles should go quite a bit further. We've increased the amount of mass, therefore increasing the amount of potential gravitational energy. It should go further. Let's see what happens. Firing increased mass, trial 1. 3, 2, 1. Trial 2. 3, 2, 1. Trial number 10. 3, 2, 1. And finally, we're going to jump ahead and see the results of our decreased mass. From there, we're going to calculate, put it in the computer, and give you the results. 1, 1, 1. Well, after analyzing the results, it can be concluded that even after we added mass to the counterweight, it didn't go all that much farther. In fact, it stayed within 5%, meaning that it was the same distance. When we decreased the mass, it did go a shorter distance, showing that in some circumstances, it does make a difference. Therefore, this myth, that increasing the mass of a counterweight always makes a difference, is busted. Oh, great year.